In our previous video, we looked at this problem of summation and approximating the area under a curve using rectangles. We did inscribed, circumscribed, and midpoint using the function f of x equals 4 minus x squared. This is what the previous problem looked like, if you may recall. And I gave you the fact that the actual area was 5 1/3. So what we're going to do today is make the transition from approximating to using summation notation to find the actual area underneath the curve. And the way we do that is by taking the number of rectangles and increasing the number of rectangles so that we reduce to the point where we almost eliminate any area either above or below the curve that is not included or should not be included with our rectangles. And when we talk about increasing, what we're going to do is increase it so that the number of rectangles approaches infinity, and that would be a limit. So one of the things we need to do is determine what is the width, and so you may recall that delta x is b minus a over n. We're going from 0 to 2, so delta x is 2 minus 0 over n. And so here's the idea, is that the first right endpoint would be 2 over n. The next right endpoint would be another 2 over n, and the next right endpoint would be another 2 over n, and so on. And what we want to do is find the height at each one of these right endpoints multiplied times the width. And we're going to take the limit as the number of rectangles, the n, approaches infinity. So again, these areas would be reduced to the point that they are getting closer and closer to 0, infinitely close to 0. And so what we want is to be moving along from one right endpoint to the other as we go from 0 to 2. And so that is where our summation notation comes into play. So the area will be the limit as the number of rectangles approaches infinity of the sum as I goes from 1 to n. Our width of each rectangle is 2 over n, and the height is the function value, so f of 2 over n I. And so when I is 1, we would go to the first right endpoint. When I is 2, we would go to the second, 3, the third, and so on, and I goes from 1 to n, however many rectangles, but n is going to infinity. So we're going to have an infinite number of rectangles, if you will, here. So here's our setup. So now we're going to use our function 4 minus x squared. So we're still continuing with our notation. So we have 2 over n, and now we're going to substitute 2 over ni for x in our function. And we're going to simplify this. Again, we're going to keep our limit and summation notation going. So that would be 4i squared over n squared. I'm going to distribute the 2 over n. And we end up with 8 over n minus 8i squared over n cubed. We're getting close to having to apply some of our summation formulas. So first, what I want to do is split this up. And the summation formulas that we're going to use, this parenthesis should have been right there. We're going to use the constant. That would be c times n. And we're going to use I squared. And that is n times n plus 1 times 2n plus 1 over 6. And so continuing back over here, so we have the constant 8, and so maybe this would actually help people a little bit, right? We can pull the 1 over and out, and I can actually pull the 8 over n cubed. And so now you can see 8 is the same as our c, and here we have the I squared. So we're going to substitute the c over n, which would be 8n here, and we'll substitute this expression for our I squared. So we end up with 8n over n. We'll simplify that in a minute. And here we end up with 8n over n cubed times, and let's bracket that, n times n plus 1 times 2n plus 1 over 6. So now this is about taking the limit as n approaches infinity of this whole term, but we're going to simplify this a little bit. So the n's divide out, so that's 8 minus, and 8 over n cubed. And when we multiply this out, we end up with 2n cubed plus 3n squared plus n over 6. And simplifying that just a little bit more, and we're going to take the limit of each term. This would be 16n cubed, 24n squared plus 8n over 6n cubed. So now we have the limit as n approaches infinity of the constant 8, which using our limit laws we know is 8, minus, and we see here that the degree of the numerator and denominator are the same. And if we were having to show all of our work for the limit, we would divide everything by the highest power of the denominator, which would be n cubed. And you'd end up with a constant 16 over 6. Both of these limits would go to 0. You'd have 24 over n and 8 over n squared. So that equals 16 over 6. And we also know, because the degrees are the same, that limit is our leading coefficients. And 8 minus 16 over 6 is 5 1/3, which is exactly what you showed you yesterday, without actually having computed it. So the exact area, by taking the limit as n approaches infinity, the number of rectangles, is 5 1/3 square units.